NotebookLM just added video, so now you can generate a video of your thing. So I have this research paper, denoising diffusion probabilistic models. So let me see the video. Let me click play.
All right, let's dive into something that honestly feels a little bit like magic. We're going to talk about how an AI can look at a screen full of just random static and somehow turn it into a beautiful, coherent picture.
It's 8
So let's
minutes.
pull back the curtain and see how the trick is actually done.
It's
Pretty
8 minutes.
much any AI image you've seen online, it starts its life looking exactly like this. And no, that's not a blurry photo. It's just pure random noise. There's nothing there. No subject, no light, no composition, just chaos. Kind of like an old TV tuned to a dead channel. And yet, somehow, from all of that nothingness, the AI creates
like this.
a whole set of incredibly detailed, photorealistic, and totally new images. I mean, just look at the lighting, the textures, the way the rooms are put together. These pictures weren't just scraped from the internet. They were basically dreamt up by the machine. So that really brings us to the core question, the big mystery we're going to unpack in this explainer. How on earth does this happen? Is the AI some kind of digital ghost in the machine creating from nothing? Or is there a really clever scientific trick going on behind the scenes? Well, the secret was finally cracked in a huge research paper back in 2020. So the official name for this technique is a mouthful: denoising diffusion probabilistic models.
Let's continue, but let me just check. Okay, it's recording.
We're just going to call them diffusion models for short. Now, the name sounds super complex, I get it. But the idea behind it is actually beautiful and, surprisingly simple. It's not about teaching an AI to be a painter at all. It's about teaching it something completely different. Here it is. This is the big secret. The AI doesn't learn how to create a picture from a blank slate. Instead, it learns how to undo destruction. It's trained to look at a noisy, messed up image and perfectly reverse the damage. And to understand how that works, we need to look at it as a two-step process. Okay, step one is called the forward process, or diffusion. This is all about training. You can think of it like this. If you want to teach a detective how to solve a crime, first you have to show them exactly how the crime went down, right? You show them over and over and over again. So look at this. During its training, the AI has shown this exact process millions of times. You start with a perfect, clean image on the right, in this case, a bird, and you just systematically destroy it. You add a little bit of noise, then a little more, and then more and more, until all you have left is static on the far left. The AI is watching every single step of this destruction, learning what a slightly noisy bird looks like versus a very, very noisy bird. And this gets us to the key.
I like this, but it's going too much in detail. Maybe we already know this, but I'll try with different papers later again.
Idea from the paper.
I like this.
A diffusion model isn't some general purpose artist. No, it's a specialist. It's an expert that's been trained to do one thing and one thing only. Reverse this.
But this needs to be adapted for different audience. So if my audience is more technical, already knows this, then this is too simple. But if somebody hearing this for the first time, it's too complex.
Very specific kind of destruction. It gets really, really good at looking at a noisy image and knowing exactly what it looked like just one tiny step before that last bit of noise was added. And that brings us to step two, the reversal. So after all that training, watching images get destroyed, the AI finally gets to show off what it's learned. This is where the real magic happens. This is the act of creation. So now we just run the whole process backwards. We start with that screen of pure random static on the left. The AI takes a look and makes its best guess. It says, okay, based on everything I've seen, this chaos looks like it came from this slightly less chaotic pattern. And it takes that tiny step back, removing just a speck of noise. Then it looks at the new, slightly less noisy image, and it does it again, and again, and again, 1,000 times, until a crystal clear image just materializes out of the static on the right. Now here's the thing. This basic idea of reversing noise, it wasn't totally new in 2020. People had tried it before, and the results were, okay, promising. But the authors of this specific paper introduced one single elegant change to the process that just unlocked the mind-blowing quality we see today. And here it is. This is the aha moment. The old way was to try something really hard. The AI would look at a noisy image and try to guess what the final clean image should look like, all in one go. The breakthrough was to change the goal. Instead of predicting the final picture, they trained the AI to just predict the noise that was added in the last step. I mean, think about it. Predicting a pattern of random static is a much, much simpler job for an AI than trying to hallucinate an entire photograph. And by just subtracting that predicted noise, the AI could clean up the image with incredible precision. So this is basically the recipe from the paper. This is the loop. Step one, you start with pure random noise. They call it XT. Step 2, the AI predicts the noise pattern it sees in that image. Step 3, you subtract that predicted noise from the image. Step 4, and this is a cool little trick, you add a tiny bit of new random noise. That just keeps things interesting and stops the process from getting stuck in a rut. And step 5, you just repeat that loop over and over, maybe 1,000 times, until a clean image, x0, has been slowly sculpted out of the static. So the big question is, did this little trick, just predicting the noise, did it actually work? Well, the results they published in the paper weren't just a small improvement. They were absolutely spectacular. They blew the old benchmarks out of the water and proved that these diffusion models could compete with and honestly even beat every other method out there.
And hey, the proof is in the pudding, right? Look at these. On the left, you've got these incredibly varied images of churches, all different architectures, different lighting. On the right, these bedrooms with just insane detail in the fabrics, the furniture, the lighting. This proved the technique didn't just work on simple little objects. It could handle incredibly complex and diverse scenes.
And it wasn't just about looking good to the human eye. The numbers backed it up. The model got a new record low score of 3.17 on a really important image quality benchmark. That number comes from something called the Frechette Inception Distance, or FID score. The simplest way to think about FID is like you have another AI that acts as a judge. It looks at the fake images and a bunch of real ones, and it decides how similar they are. A lower score means the AI judge is having a hard time telling the fakes from the real thing. And at the time, 3.17 was the best score anyone had ever got. But honestly, this might be the most mind-blowing result of all. What you're seeing here is a smooth blend and interpolation between the person on the far left and the person on the far right. And look closely, it's not just fading from one picture to another. It is smoothly blending concepts. The pose changes, the hairstyle morphs, the facial structure transforms. This is a huge clue that the AI isn't just memorizing pixels. It's building some kind of internal map of what actually makes a face a face. And all of this leads us to the bigger picture here. This breakthrough was way more than just a neat new trick for making pretty pictures. It started pointing towards something much, much deeper about how machines can actually understand the world. The authors themselves bring up this incredible idea called conceptual compression. Think about it. For the model to create a totally new, unique bird from nothing but noise, it can't just be storing a bunch of photos of birds it's seen. It must have learned a compressed, essential idea of birdness. You know, the abstract concepts of what a beak is, what feathers are, how wings work. It's almost like it's learning the essence of things. So in the end, the impact of this one paper to send a shockwave through the entire field of AI. It kicked off a whole new way of thinking about generative AI. It gave us the tools that artists and photographers are using every single day now. And it even pointed towards new ideas in data compression. And of course, it forced all of us to start asking some pretty big questions. And that's really the question we want to leave you with, one that the authors themselves brought up. As this technology just gets better and better, we have to think about what it all means. If a machine can create beautiful, genuinely new art from just noise and data, what does that mean for the future of human creativity? What is the role of the artist in a world like that? It's something to think about. Thanks for watching.
Nice, I like this. This just needs to be adapted, maybe with some prompt engineering, but they don't let me do any prompt engineering on the video. So maybe if I make a PDF file where it's gonna read that PDF file and it's gonna read the text, so I can maybe put some prompt in there. And then I can put some images. How do I make sure when I use this tool that videos are good? So I'm thinking I need to create a good PDF file and put some prompts and tell it how to explain, because I cannot edit the video or have like any influence even there. Anyways, I'll be trying this more and making more videos. So see you next time.